Today, we're going to demystify one of the absolute most elusive, but honestly visually captivating concepts in all of organic chemistry. If you've ever looked at a chemical diagram and just kind of felt like those molecular structures are keeping some massive secret from you, well, you're in exactly the right place. We're going to look way beyond those static, boring drawings on a chalkboard and uncover the dynamic, frankly beautiful reality of how molecules actually hold themselves together. But to kick us off, I want to ask you a seemingly simple question about the subatomic world. So where do electrons actually live? See, when we look at a molecule, it's incredibly tempting to think of it exactly like an architectural floor plan. We tend to imagine that every single electron has a designated permanent little room that it just stays in forever. But the quantum world absolutely does not work like rigid architecture. The reality is that electrons aren't always confined to a single tiny permanent space between two atoms. I mean, we've all been taught classic Lewis structures, right? Where electrons are neatly trapped in these fixed, rigid lines drawn on paper. I actually like to call this the Lewis lie. Now, okay, it's not that these structures are completely wrong, but they definitely aren't the whole truth. Lewis theory forces electrons into these localized, rigid bonds. But the physical reality, the reality of resonance, is this gorgeous, delocalized cloud of sharing. Because when electrons are allowed to spread out across multiple atoms, they literally jump at the opportunity. So, here's our roadmap for the explainer today. 1. The electron prison break. 2. The hybrid reality. 3. Rules of the escape. 4. Ranking the contributors. And finally, number 5, the shape of life. All right, let's dive right into part 1, the electron prison break, escaping those rigid lines. So, why exactly do electrons want to escape their localized bounds in the first place? Well, it all comes down to the universal law of energy. Think of it exactly like this. One person trying to carry 100 kilograms? Yeah, they're going to collapse from exhaustion pretty fast. But 10 people carrying 10 kilograms each? They can carry that all day long without breaking a sweat. Resonance is the exact same concept, just applied to electrical charge. It's literal burden sharing. When electrons stop belonging to just one atom and get to spread out over multiple atoms, it significantly lowers the overall energy of the molecule. And in the world of chemistry, lower energy always means greater stability. This brilliantly illustrates how those standard Lewis formulas can be so misleading, trying to force electrons into localized positions when what they actually crave is the space to share the burden. Moving on to section 2, the hybrid reality, blending the structures. Let's see how this builds into the physical structure of the molecule itself. Because, okay, I need to bust a massive myth for you right now about what electrons do when they finally break free. A lot of people think resonance is some sort of rapid flip-flop. They think it's an oscillating pendulum swinging back and forth between different states so fast that it just looks like a blur. No way. The reality is a single, permanent, blended state that we call a resonance hybrid. The individual resonance structures we draw on paper, those are just the maps trying to describe a landscape. The hybrid is the actual physical landscape itself. Stable compounds do not rapidly switch between theoretical states. They exist uniformly, inheriting a perfect blend of features from all their resonance forms. And the impact of this is absolutely staggering. Look at this massive number, 152 kilojoules per mole. That right there is benzene's exact extra resonance energy. If benzene's double bonds were rigid, it would behave in a very predictable, highly reactive, and, quite honestly, pretty unstable way. But because those electrons form a giant continuous ring of sharing, the molecule gains an immense 152 kilojoules per mole of extra stability. Thanks to the secret democracy of sharing, it becomes an incredibly stable, completely different beast. And because these electrons are actively smeared out across multiple atoms simultaneously, we get the crazy concept of fractional bonds. You can officially say goodbye to the idea that bonds are just strictly single, double, or triple. In a resonance hybrid, you might actually have a 1.5 bond, or even a 4/3 bond. A 1.5 bond is stronger and shorter than a single bond, but it's weaker and longer than a double bond. It is quite literally the perfect blended average of its parent structures. Which brings us to section 3, rules of the escape, tracking the electron flow. So if electrons are constantly smearing into these fascinating fractional bonds, how on earth do we track them? To make sense of all this quantum chaos, we absolutely need a systematic map. To map the escape, we follow a strict set of cardinal rules of electron mobility. First, the molecular skeleton. The physical atoms and their single sigma bonds stays completely put. Never move them. They are your concrete foundation. Second, only pi electrons from double or triple bonds and unshared lone pairs get to move. And third, you can never ever change the total charge of the molecule. So the crucial point here
is that while the rigid sigma bonds hold the house together, the pi bonds and unshared pairs are the mobile units completely free to hunt for better real estate to lower the molecule's overall energy.
We track this precise movement using a standardized shorthand known as curved arrow notation. These curved arrows act as the exact map for electron traffic. Remember our golden rule. They track the movement of electron pairs, never the atoms themselves. The tail of your arrow always originates right where the electrons currently sit, an area of high electron density like a lone pair or a pi bond. And the pointed head of the arrow shows exactly where that specific pair of electrons is going to form a new bond or become a brand new lone pair. But it's almost never just a single arrow. Pushing a new electron pair toward an atom usually forces an existing pair to jump onto an adjacent atom. Why? To avoid violating the octet rule. Think about it. If a carbon atom already has 4 bonds and you push a new pair of electrons right at it, it has to kick an old pair away so it doesn't end up with 5 bonds. It's this beautifully synchronized subatomic dance. You push a pair, you kick a pair.
Okay, section 4, ranking resonance structures, the hierarchy of stability.
Once we map out all these possible structures, we have to face a pretty harsh truth. Not all resonance structures are created equal. A resonance hybrid is going to look a lot more like its most stable contributing structures. To spot the major contributor, meaning the structure the real molecule looks the most like, you have to methodically run through this exact hierarchy of stability. Step 1, ensuring every single atom has a full octet is the ultimate stabilizing factor. Full octets will beat everything else, hands down. Step 2, if you have them, you absolutely want to minimize formal charges as much as possible. And step 3, if you absolutely must have a negative charge somewhere, it belongs on the most electronegative atom. Put it on oxygen, not carbon. And this brilliantly illustrates how these subatomic ranking rules dictate the macroscopic reality we interact with every single day. Like, have you ever wondered why vinegar, which is just acetic acid, is incredibly acidic, but the regular alcohol sitting in your cabinet isn't? It's resonance. When acetic acid loses a proton, its conjugate base, the carboxylate ion, takes that negative charge and spreads it beautifully across 2 highly electronegative oxygen atoms. That massive burden sharing stabilizes it so much that it is perfectly happy to just let that proton go. And finally, section 5, the shape of life. Resonance in the real world. I want to zoom all the way out from the subatomic smearing on a chalkboard to explicitly show how this concept actively dictates the biology of your very own body. Think about the proteins in your body. They're made up of amino acids linked together by amide, or peptide bonds. And if we look at the structure of an amide, we see how the nitrogen atom so willingly donates its lone pair of electrons into the adjacent carbon-oxygen bond. Because of this exact resonance, those peptide bonds gain a powerful partial double bond character. So what does this subatomic refusal to be tied down actually do for you? Well, it restricts those bonds from rotating freely. It forces them to be completely rigid and planar. This actively holds the incredibly specific 3D structural foundation of the proteins that make up your tissues, your enzymes, and all of your DNA machinery. Without this subatomic burden sharing, without resonance locking these shapes into place, biological chemistry as we know it would literally just collapse into chaos. It really isn't an exaggeration to say that life itself depends on resonance, which leaves you with a pretty profound thought, doesn't it? If the simple smearing of invisible electrons, shifting just slightly to share a burden and lower their energy, completely shapes our entire biology and the physical world we can see and touch, what other quantum secrets are actively dictating the macroscopic world around us right this second? It's wild to think about.